Okay, so we start this section on Bayes' rule by the following definition. The definition of partition. A collection of sets or events. A collection of sets or events, B1, B2, Bn, is said to be a partition of a set S or of the sample space S if the sets are mutually exclusive and their union is the set S or the sample space S. So for us, the sets are events and S is the sample space. But this definition works generally for any set of any collection of sets and a set big set S. Now, so once again, basically what a partition is, a partition divides the sample space into mutually exclusive events. Okay. An example of a partition would be okay, so an example of a partition would be the following. If you have the sample space S, so think of S being the sample space. Sample space, and let B be an event, so that means B is a subset of S. So B is an event. Then notice that B union B bar, B union the complement of B is equal to what? 1. B union B complement is the entire sample space, right? B complement contains everything outside of B, right? So B union B complement is always the sample space. Is everybody okay? So basically then, B complement is a partition of S. So if I look at the collection of events, B complement, this is a partition. This is a partition of S. Is that making sense? Is everybody okay with that? B comma B complement, that's a partition of S. Again, there are, you can partition the sample space in many different ways, right? So just to give you another example, if I have, let's say toss a coin twice, in that case the sample space is what? H T T. Now if I take the events A to be the event of getting 2 heads, B is the event of getting 2 tails, and C is the event of getting exactly a head and a tail, right? Now notice that ABC constitute a partition of S. So A comma B comma C, this is a partition of S, right? Why? Because A, B, C, they are disjoint, aren't they? They are disjoint, and their union is the entire sample space, right? A, B, C are disjoint, and their union is the entire sample space. Now, if I change, let's say B, let's say I change B by writing TH here. Okay, is ABC a partition anymore? If I change B, now B has TH as well. Now ABC is not going to be a partition, right? Why? Because they are not mutually exclusive. Even though their union is still the sample space, their union is still the entire sample space, but they are not mutually exclusive. Okay? So a collection of events is a partition of the sample space if they are mutually exclusive and their union is the entire sample space. Okay, so remember that. Let me erase this example here. I need the space for other purposes. Okay, so first I have the average rule here. So what's the average rule? The average rule says the probability of A is the same as the probability of A given B multiplied by the probability of B plus the probability of A given B complement times the probability of B complement. Okay? Now I'm going to give you a proof of this in a second. First of all, the way I'm going to interpret this equation is by saying that the left-hand side is the overall probability of A. The left-hand side is the overall probability of A, and I can think of the right-hand side as the weighted average of the conditional probabilities of A, right? Where the weights are given by the probabilities of the conditions B and B complement. Okay. Notice that the conditions B and B complement exhaust the entire sample space, right? B complement is a partition of S. So B complement exhausts the outcomes of the sample space. So the right-hand side can be interpreted as a weighted average of the conditional probabilities of A with respect to B and B complement, where the weights are given by the probabilities of the conditions. Right? Notice that the probability of B plus the so if I am thinking of these two as weights, right? I am thinking of this guy as weight 1 and this guy as weight 2. Notice that weight 1, W1 plus W2 is 1. So I can think of W1 and W2 as weights. Okay, I can think of the right-hand side as a weighted average. Is that making sense? Okay, so now how do I prove this? Let's try to prove it. I have the Venn diagram in front of you. The green region is the intersection of A and B. The yellow region is B complement, right? And A and B are also labeled. So notice first of all that I can write A I can write A as A intersect B. What is A intersect B? A intersect B is the green region, right? Union A intersect B complement. What is A intersect B complement? A intersect B complement is the red region, right? So is it clear that I can write A as the union of A intersect B and A intersect B complement? Notice that this union is a disjoint union, right? This event and this event are mutually exclusive. So I have written A as the union of two mutually exclusive events. So therefore I can say that the probability of A is the same as the probability of A intersect B plus the probability of A intersect B complement. I could do this because the two events in the union are disjoint or mutually exclusive. Now what can I do? Well, now I apply the multiplication rule. By the multiplication rule, what is probability of A intersect B? You guys remember the multiplication rule? What's the probability of A intersect B by the multiplication rule? You must have multiplication rule in your notes. Given B times the probability of B plus the probability of A given B complement times the probability of B complement, right? So this is where we apply the multiplication rule, right? And so our conclusion is, so the probability of A is indeed the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. So this is known as the average rule. The way I say it in words is that the overall probability of A is the same as the weighted average of the conditional probabilities of A with respect to conditions B and B complement, where the weights are given by the probabilities of the conditions. So I think of these two conditions as weights, okay? These two conditions, B and B, I think of P of B and P of B complement as weights. So then the right-hand side can be thought of as the weighted average of the conditional probabilities. You guys know what a weighted average is, right? I keep saying weighted average, but so if I have three quantities, let's say I have three quantities, X, let's say I have three quantities X, Y, and Z. These are three quantities. If I multiply them by W1, W2, W3, right, where W1 plus W2 plus W3 is equal to 1, right? Then this is the weighted average of X, Y, and Z. If W1, W2, W3 sum up to 1, then W1x plus W2y plus W3z is the weighted average of x, y, and z. So you can think of W1 as the frequency, as the relative frequency of x. Okay? Think of W1 as the relative frequency of x. That is, W1 is the proportion of times x occurs in the data. W2 can be thought of as the proportion of times y occurs in the data, and W3 is the proportion of times z occurs in the data. Is that making sense? So then if you look at this quantity, then it's the weighted average of x, y, and z. Is everybody okay? All right, so generally, what can we say? Well, the general average rule is the following. The general average rule says, suppose that B1, B2, Bn form a partition. Wow, partition. Partition. Okay. That's a common mistake that I always make. Partition of the sample space S, then the probability of A is the same as the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 plus probability of A given Bn times the probability of Bn. Once again, the left-hand side is the overall probability of A. The right-hand side can be thought of as the weighted average of the conditional probabilities of A with respect to conditions B1 up to Bn, where the weights are given by the probabilities of the conditions.